I'm excited that you're part of this program. I have been a fellow for Sinai Synapses, which brought together scientists, rabbis, and media communications people, and was before they expanded into the synagogue world, were bringing us all together as thought leaders in this area of science and religion coming together. And I think it's extremely important that synagogues, churches, mosques, that all of us think about what are the places of religion, where does religion and science talk to each other, and how do they influence each other in different ways. And I say that, and I then move to my introduction of Jews and politics, rabbis and politics. In the 21st century America, with separation of church and state, with IRS tax rules for religious nonprofits avoiding political endorsements, we generally see the two as separate realms, not to be crossed. At election time, especially, we get angry when we hear preachers or teachers or rabbis overstepping boundaries of political debate. But throughout history, rabbis have always been implicated, embedded, and involved in the politics of the day. This began as far back as the start of the rabbinic period and has influenced Jewish thought and development ever since. In a pretty famous passage you may remember from the Passover Haggadah, 4 second-century rabbis are holding a Seder in Bnei Brak. They discuss the Exodus story all night until their disciples come to them to announce that it's time for the morning Shema prayer. One can read this story as showing the intellectual and spiritual zeal of the 4 rabbis who were studying all night and hadn't even realized sunrise had come. But many modern scholars also see a different context to this tale. Why did their students have to tell them the sun had risen? Perhaps the rabbis did not see the sunrise because they were hiding in a cave or a bunker. What were they really doing there? Perhaps they were plotting resistance against Rome. It's time for the morning Shema was a code meaning the Romans were approaching. The Seder then in this context is more than a recounting of the miracle of the Exodus from Egypt. It recalls a defiance to Roman oppression. Passover and Haggadah becomes more than a celebration of liberation. It seems to be a call to resistance. Rabbi Akiva, one of those 4 rabbis holding the Bnei Brak all-nighter, is known from rabbinic sources to have been active in the Bar Kokhba rebellion of 136 CE against Rome. He believed that Bar Kokhba was the Mashiach, though some other rabbis openly ridiculed him for that belief. When the Bar Kokhba rebellion failed, Rabbi Akiva was taken by the Roman authorities and tortured to death. Not every rabbi was ready to raise arms against Rome. Earlier in the Roman era, tradition describes Rabbi Yochanan ben Zakkai as a pacifist. In 68 CE, when Jerusalem was controlled by the Jewish zealots and under siege by the Roman general Vespasian, ben Zakkai urged surrender, but the zealots would not hear of it. According to the Talmud, Rabbi Yochanan ben Zakkai faked his own death and had his disciples smuggle him out of Jerusalem in a coffin. They carried the coffin to Vespasian's tent, where ben Zakkai emerged from the coffin. He told Vespasian that he'd had a vision. Others would call it a shrewd political insight, that Vespasian would soon be emperor. And he asked Vespasian to set aside a place in Yavna, where he could move his yeshiva and study Torah in peace. Vespasian promised if the prophecy came true, he would indeed grant ben Zakkai's request. Vespasian became emperor and kept his word, allowing the school to be established after the war was over. The yeshiva survived and was a center of Jewish learning for centuries. The survival of Judaism, the teachings Jewish law gives about external authorities, how we celebrate our holidays, even how Judaism has confronted outside cultures, have all been shaped by the politics of the early rabbinic period and of each period since then. It's why the Talmud is not simply a law code. Stories and histories are included and expounded. No person, no study, no pursuit, no practice, no scientific study can be separated from the political atmosphere and reality of its creation and time. This is what David will explore today for and about Albert Einstein, how the politics and political history of the 20th century affected Einstein's pursuit of general relativity. We'll all be introduced to what he describes as surprising linkages. David Kaiser is the Germasenhausen Professor of the History of Science and Professor of Physics at MIT, where he also served as inaugural Associate Dean for MIT's new cross-disciplinary program on social and ethical responsibilities of computing. He's the author of several award-winning books about modern physics, including How the Hippies Saved Physics, Science, Counterculture, and the Quantum Revival, and Quantum Legacies, Dispatches from an Uncertain World. A fellow of the American Physical Society, David Kaiser has received MIT's highest awards for excellence in teaching. His work has been featured in Science, Nature, the New York Times, and the New Yorker magazine. His group's recent efforts to conduct a cosmic bell test of quantum entanglement, together with Nobel laureate Anton Zeilinger, were featured in the documentary film Einstein's Quantum Riddle, which premiered on PBS in 2019. It's with pleasure that I invite David Kaiser up to address us today.
Thank you, everyone. I'm really just so delighted to be here. Science with the Shapiro, first of all, what a fantastic name and a great idea. I want to thank my very dear friend Joe for inviting me, and Rabbi Fisher as well. Great colleagues for a long time. And it's my first visit to this beautiful temple and the congregation. So thank you all for coming on a Sunday morning. It's amazing to hear about black holes and the Big Bang and Einstein, and lots to dig into. So as Rabbi Fisher mentioned, I'm going to talk very much along the theme we just heard about the embedding of some work that I still find just sort of, it gives me chills how beautiful this work is, I think. And yet to see that it was embedded all along in a very messy, sometimes not such a beautiful or pretty series of political developments. So I want to talk about Einstein's legacy, studying gravity in war and peace. So I'm going to start. It's remarkable, you might have a trip to see the Haystack Observatory soon. I was going to start with Haystack already. This photo, you might have seen it. This is impressively clear, although it looks kind of blurry. That's a black hole that's many light years away from us. Completed and published just recently in April 2019, including data from this nearby observatory, really in our backyard. So these days, people all over the world were interested in gravity and how our universe has been changing over the last 14 billion years. We get to study things like black holes, these sort of chirps, capturing the kind of roiling, rippling fabric of space and time themselves as gravitational waves captured by groups like LIGO, or even this kind of afterglow from the Big Bang. We call it cosmic microwave background radiation. We have amazing inputs. They're all sort of strung together in our thinking in this framework that Albert Einstein introduced just over 100 years ago, called the General Theory of Relativity. The theory is really very beautiful. Theory of gravity. And so I've been interested in a long time in gravity, interested in Einstein, and given this sort of extraordinary wealth of cool new stuff we get to think about in recent years, wondering how did we get there? How did this legacy kind of get introduced, and how has it changed over time? And there again, we, just as Rabbi Fisher was saying, we have to step back and think about not only these sort of austere, otherworldly phenomena like black holes, the Big Bang. We have to start asking about who are the people and the times and places where they were putting all these ideas together. So I think when a lot of us think about Albert Einstein, we probably have a picture like this in mind. I certainly did for a long time. So Einstein pictured later in his life, alone. All he seems to need is quiet, first of all. He wants to be alone in his office with maybe some paper and a pencil, but basically just stay at, right? Sort of aloof from the sort of raucous daily life. Here he was at the Institute for Advanced Study in Princeton, New Jersey. And yet this sort of carefully cultivated image, and Einstein himself really helped to further, of him being kind of apart from the world, separate from the world, that really doesn't hold up very well. It turns out he was an immensely political person for his whole life. very bravely as a young person around the time the First World War broke out in Germany, right up to the very end of his life here in the United States in the mid-1950s. He was outspoken, he was active, he was a left-leaning, kind of vigorous activist. And don't take my word for it, the FBI tailed him for 20 years because they were worried that he was such an outspoken radical. So there's an FBI file based on all kinds of, at the time, largely illegal wiretaps and all that stuff like that now we can all download for free to the internet, released through Freedom of Information Act about 7 years ago. So we have a series of documents that seem to fit very poorly with this picture of Einstein as sort of separate from the hustle and bustle of everyday life. He himself was a thoroughly political creature, often fighting for causes I still think we should be fighting for today. Some really interesting scholarship by other colleagues on that. So Einstein, the image as being separate from politics really doesn't sit so easily with really a lot of other influence about how he spent his time. So that made me wonder about this greatest of his scientific legacies, the General Theory of Relativity. That's also often cast as sort of apart from the kind of foibles of everyday life and the political realities. And it's not just what people said in passing, there's some really wonderful depictions of that aloofness. This was called the Temple of Relativity. That was more like the Taj Mahal than like But the idea was that to be kind of austere monuments to stand apart up on the hill, not in the flux of daily life. You can see in the dome here, I'll say more about in a moment, the famous equations of this theory carved into the marble. But it's meant to be a kind of statue, separate, beautiful, but not sort of in the mix of things. And other people would kind of make similar comments. There's a quotation from a very influential textbook from some time ago by mathematical Singe. He says, of all the physicists, the general relativist has the least social commitment. Let the relativist rejoice in the ivory tower, or indeed in Westward, where he feast to seek understanding of Einstein's theory, as long as the busy world is satisfied to do its job. Now, that sounds like the picture of Einstein alone in the audience. That doesn't really hold up either. And so what I've been trying to do with this long-running research project is look at some instances where we want to understand how relativity has been introduced, developed, blossomed into this amazing scientific theory, not by treating it separate from the world, but again, exactly as Rabbi Fisher was saying, is seeing it as always a part of the world. Sometimes a very messy world, but nonetheless never really a part. So today I'm going to talk in 3 sections. Joe said there's a 9-hour session. I think that's not right. But there's plenty of good. So I'm going to talk about 3 main sections. I want to introduce some of the main ideas that Einstein himself called the happiest thought in life. That's a pretty good endorsement. The guy had a happy life. This is the happiest. So what were some of his thoughts that led to the general theory of relativity? And then we'll step back a little bit and say, well, what was the world in which he was doing this? What were his immediate circumstances? How was he communicating with colleagues and trying to spread these ideas? And that was still going on roughly 100 years ago. So we'll start back in not quite 700 years ago, but some time ago. And then I want to zoom forward a bit more to this last bit and look actually close at home, literally, looking in our own backyard, actually in places like Haystack, at places like MIT, and more in the years after the Second World War, not just in the early years around the First One. So that's what I want to share with you today, and we'll jump in. So Einstein worked on what became his general theory of relativity for about 10 years. This was a remarkable intellectual journey. And what's really fun for people like me is that it's also really well documented. We have an amazing range of sources from that time. We can follow Einstein's ins and outs as he worked in a small circle of colleagues. We have things like his personal notebooks from key moments. I love these because he was kind of a dummy. Einstein was not always such Einstein. All kinds of errors, scratching. I show this to my students all the time. Like there's hope for us. Right? Einstein made all kinds of really pretty silly mistakes. Mostly because he cut all his math classes in college. Also a good lesson. Don't do that. Anyway, we also, in addition to his notebooks, we have letters, his correspondence, notes from other scholars, drafts of essays. We have a lot of documents to show really almost day by day, certainly month by month, how his thinking was evolving. And so we know that it took him really the better part of 10 years of really intense work to get to what became this now sort of crowning achievement, the general theory of relativity. I won't reproduce all those 10 years in real time, because there's only so much food. Yeah. I'll cut to the chase. Where he gets to is this extraordinary expression. I often tell my students, maybe I shouldn't, if they're in the market for new body art, like a tasteful tattoo, you could do a lot worse. Okay? Look at this. More interesting, you can tweak this. It's just fantastic. I'm going to unpack that for us as he says. But it's really going to boil it down to his 10 years of really hard thinking to say that basically this shape of space and time depends on where the stuff is, on the distribution of matter and energy. I'll go through that in a few more steps. That wasn't obvious to Einstein for a long time. It's probably not obvious to all of us in this room, but that's what this sort of endpoint of this journey was, relating the kind of shape of space and time, which is what's quantified, it's made you make a mathematical geometry here, and this way to the distribution of where this stuff is. So how to get to that? Why do you think that was at all likely? Here's what he called the happiest thought of his life. Starting around 1907, which again we know from this great documentation, he was sitting at his day job. You might know in the early years, Einstein, because he cut classes, it was kind of obnoxious, couldn't get the job he wanted, also lessons than that. So he was aiming for a university professorship. He didn't get one for years and years and years. And instead, he got a job as a patent clerk in the Swiss Federal Patent Office at Bern. He was a civil servant. He started out as patent clerk, third class. There was no fourth. This is really just starting at the bottom. So his day job was to go over patents, should this patent be granted or not. At one point, because he wasn't really paying attention, he tells the story. He was staring out the window, and he saw basically a window washer fall from several stories up. And says, don't worry, the window washer will sort of land in a canopy instead of splattering on the pavement. It was okay. But what he wanted to focus on was during the fall, he was sort of saved by this fabric. What would that person have experienced during the fall? So if he let go, for example, of his bucket and his squeegee, they would actually sort of hang suspended. They would fall at the same rate as he did. So the bucket would not fall further from his hand. It would sort of appear to hover. Whereas if the window washer were at rest on the ground and let go of the bucket, of course, the bucket would fall. It would not stay the same sort of position relative to his hand. So Einstein began to realize that during this fall, gravity would sort of would fail to matter to the person who's falling. It would be an interchange between acceleration, falling toward the ground, being sucked by gravity, and gravity itself. So as he wrote here, for an observer in free fall from the roof of a house, like this unfortunate window washer, there is during the fall no gravitational field. So somehow he convinces himself that gravity and acceleration should be interchangeable, really from thinking about just everyday processes like this, not being driven by the mathematics at first. And somehow gravity and acceleration, which we think of as totally separate things, what if they're actually exchangeable? What if they're versions of the same thing? Einstein calls this the equivalence principle. There's an equivalence between a certain state of motion, speeding up, acceleration in this case, and gravity. Okay. A few years after that, he's still thinking about these very kind of cartoonish pictures in his mind. And then he starts to think about a scenario like this, not only in something he sees out the window front on his office, but now he's thinking about a more fantastical notion. What if there's a spaceship made out of windows so you can see outside? And while the spaceship has its rocket firing, so it's accelerating upwards, speeding up in its trip, a light beam enters nearer the ceiling. And then how would the light beam traverse this scene? Well, as at different moments of time, as the rocket's firing, the ship is accelerating, speeding upwards, it would appear as if the light beam enters near the ceiling but exits near the floor. Right? So inside the ship, to an astronaut who's just in the ship, she would see the light beam start up near the top, up there, but exit down there, right? And that would be, we'd say, because the ship itself was accelerating as the rocket was firing. But he had just convinced himself that there's some deep connection between acceleration and gravity. So he said, because of this thing he calls the equivalence principle, the same phenomenon should occur even if the ship is not firing its rocket at all. What if the ship is at rest, but it's near a large mass? What if it experiences a large gravitational field? That should have the same exact effect. You shouldn't be able to tell, just like a falling window washer. And so if during acceleration, a light beam could bend its path, then gravity should also be able to bend the path of a light beam. He hasn't convinced the world of this, he's convinced himself so far. So he says gravity must be able to bend the path of light. Because he's thinking through, and again, these very kind of simple mental images and pictures. He hasn't really begun to quantify this yet. But now he gets really excited. Now we're moving into 1907, 8, 9, and beyond. Really just won't let these ideas go. Now, why was he excited about gravity bending the path of light? I think society, but anyway, you might not. It's not a 70 yet. He'd already convinced himself back in 1905 when he was a third-class civil servant that light was special. It's still in the heart of his work of what became known as the special theory of relativity, published as a young unknown researcher in 1905. So to Einstein, light was special. Nothing travels faster than light. It's the ultimate speed that it already gives itself. And everyone agrees on its speed. That part is even more mysterious. So if nothing can travel faster than light, even in principle, then light becomes a kind of mapping tool. Light, the path of light should travel the shortest possible distance from here to there. Nothing can get from here to there faster if nothing can travel faster than light. Moreover, we'll all agree on its speed. It's giving us a kind of objective measuring tool or a mapping tool. So now, if we can have these weird scenarios where gravity can bend the path of light, maybe that's really telling us not about light, but about the space through which light is traveling. Maybe light is a tool just to map for us the shape of space. So a light being's path is curved by gravity, Einstein begins to wonder, is that like saying space and time themselves are curved by gravity, and light's just showing us that curvature, revealing the curvature. Because gravity's bending light, light's special, we use it to map. So he's working this out in 1909, 1911, so I'm skipping ahead, right? It's 10 years of this stuff. Okay. So by the end of this journey, by the end of 1915, in fact, by the fourth Thursday of November of 1915, that's how we know what was going on here. Literally, the last Thursday of the month of November, 1915, Einstein comes to the form of the theory that we still use today, the form we even recognize. It really is worth getting attention to. He concludes that gravity was nothing but geometry. So there's no force of gravity at all. There's stuff like large masses, like the sun, like the earth, like the moon, like maybe even more massive galaxies, that are warping their space and time around them. And then other stuff is moving as straight a line as it can around them. So what he comes to conclude when we think about the motion, say, planets in our solar system, it's not that the sun is tugging on the earth and sort of exerting a force. It's that the sun is making a big dent in its surroundings. It's changed its own environment, the space and time around it. And then the earth is just moving as straight a line as it can in a space that's no longer is curved. Space is no longer flat. And so the earth is being affected in its motion, not because of a force, like Isaac Newton said, but rather because gravity itself is just geometry, all about the shape of space and time. I find that pretty amazing. It's important to say not just space, it's really warping the time as well. These cartoons that you might have seen before, it looks like a kind of warped trampoline, like a bowling ball in the center. That helps me think about the warping of space. What was really important for Einstein is actually warping time as well. I love these paintings by Salvador Dali, but sort of, the clocks sort of melting and warping as well. Then Einstein, by the end of this journey, certainly at the beginning, was convinced that both space and time would be warped, be distended, physically pushed out into a different shape by the presence of large masses. Where the stuff is going to bend the space around it, that'll change the object of motion through that space. There's some really, really wonderful books on this. I know we are the people of the book, so here's more books to look at for beach reading and so on. It's great books by friends and colleagues, by other scientists and by historians of science. There's a lot about this kind of journey that I'm really fascinated. These are very accessible books, some really bestsellers, so I'd be happy to chat more about all that. So that was a kind of lightning review of Einstein's own intellectual journey between around 1905 and 1907 and the very end of 1915. And he gets to this sort of really stunningly original idea of the cosmos, that it's not about forces, it's actually about stuff changing the space-time around it, other stuff moving through, and that, he says, should explain these sort of everyday occurrences like a person falling from a roof or the earth orbiting around the sun. Now, I mentioned that this was coming together in the very late months of 1915. And as you might remember, the late months of 1915 were not a very easy time where Einstein was working. The First World War, the war that was to end all wars, which did rather poorly, the First World War had broken out in August 1914, about a year and a half into a massive, unprecedented war in the middle of Europe, right when Einstein was doing all this work. So here is a map of Europe in 1914. Einstein at this time was working in Berlin, and I want to now focus in the second part of how did these new, very strange-sounding ideas about the warping of space, the bending of time, how did those ideas get beyond Einstein's own head, as he sits at his desk by now in Berlin, to colleagues in other parts of the world when suddenly moving people, let alone even sending mail, was a big, big, difficult thing to do, as Europe was already now more than a year into this calamitous horror. So what's the setting in which Einstein himself is working this stuff out? Okay, so one of the very first people to learn about Einstein's ideas was a Russian mathematical physicist, mathematician named Freundlich, who was from St. Petersburg, but was on a kind of fellowship in postdoc in Göttingen in Germany. Not in Berlin, not where Einstein was, but where Einstein has a number of friends and colleagues. We know from Einstein's diaries, his letters, all these great documents we have, Einstein was making frequent visits to Göttingen. Even after war had broken out, he'd spend 2 weeks and stay on the couch of his friend. We know a lot about his visits there. And that's when he actually met Freundlich, as Einstein himself was in the midst of working out these ideas. As I say, it took a long time. So what happens is Freundlich is very excited about these ideas. He's very mathematically adept. He begins learning all he can from Einstein's visits, and then he can't leave. Because once the war breaks out, he's a Russian in Germany now, they're at war. He's interred as a civilian prisoner of war. Now he has powerful friends, these great, great powerful professors. At one point, that was on oxymoron. Great powerful professors. Learn a lot of history. Anyway, he really was protected. He was treated much better than many others. So he was not able to leave. He was more comfortable than many others in otherwise very difficult times. And he's able to keep talking with Einstein. But Einstein still visits Göttingen. Einstein can travel within Germany even after the war breaks out. He's a German civil servant. He can go from Berlin to Göttingen. And Freundlich just can't leave. And so he has an opportunity to keep kind of learning more and more of this because, frankly, what else could he do? After the war was over, Freundlich was able to return to his native St. Petersburg, which by this point had become either Petrograd or Leningrad. I forgot the order. So by this point, the Russian Revolution had happened. He goes back to a rather different hometown left. And he begins to teach the first generation of experts in this new stuff within Russia. So some of these names might be familiar to some of you. He teaches, for example, Alexander Friedman, who helps invent basically the Big Bang model, some of the most important work for it. He teaches all these leading figures, including Lev Landau and Landau Kaiser. So we have a sort of all the transmission of these ideas where someone is literally unable to leave a place he just meant to visit, is able to learn things that few people else in the world can hear about, and then only later, a few years later, he's able to go and then teach his now local colleagues. Here's another example of trying to spread kind of working knowledge of Einstein relativity away from Einstein himself. This now is another effort to go kind of eastward. So throughout this period when Einstein was working on what would become his general theory of relativity, he would often talk with his nearby colleague Carl Schwarzschild. Schwarzschild was both an astronomer and a mathematical physicist, based pretty close to Berlin. And when the war broke out, Schwarzschild, at the age of 40, volunteered to the infantry. He was such a kind of devoted patriot. He was a Jewish man devoted to Germany, and actually volunteered for the army, and was sent to the Russian front to fight. I mean, this is an unbelievable world-class mathematical physicist and astronomer, and they handed him boots to say, So that's what he's doing. So because he's in the German army, he can still trade mail with Einstein. He couldn't if he was just in Russia. I mean, he was in Russia and the German army. So they had mail to go back and forth to places like Berlin. So Einstein's sending his friend Schwarzschild updates on Einstein's own thinking, little reprints, notes, letters, basically as a diversion for Schwarzschild. Otherwise, really stuck in literally in the muck, this muck, horrible conditions on the Russian front. Einstein was convinced that no one would ever be able to solve his equations exactly. They look so complicated, we could approximate them, we get a pretty good idea, but he thought these are just never going to solve them. And Schwarzschild writes back, because they can send mail, I solved it. And so Schwarzschild literally, as like downtime, one horrible, uncomfortable situation on the right front, finds the first exact solution of Einstein's equation. We still use it today. That's how we describe quantitatively, for example, the motion of the Earth around the sun, or even things more exotic like black holes. That's called the Schwarzschild solution. This guy. Okay, so Einstein said that's, first of all, good for you. Good job. I'm a little busy right now on the Russian front. I'll help you publish a paper. So Einstein arranged for Schwarzschild's solution to be published in one of the leading German journals while Schwarzschild was otherwise busy and rather occupied. Unfortunately, this amazing breakthrough was short-lived because very soon after that, Schwarzschild contracted a horrible skin disease and died at the front. Remember, this is war. This is a horrible, bloody, messy time. So Schwarzschild is sort of diverting himself by playing around with these equations, making that Einstein himself hadn't been able to do. And then literally weeks after that is dead in his early mid-40s. Okay, that's effort number 2, to spread working knowledge of Einstein's work beyond Berlin itself. Let me do one more effort to spread this stuff eastward. One last example from the middle of the world. Einstein had a younger colleague he also enjoyed talking with during his time, named an astronomer, Freundlich, based right in Erwin. And Freundlich was very excited. He was actually an observational astronomer. Einstein was a thinker, a theorist, but not, he wasn't putting his eye to the telescope. Freundlich really was. And so Einstein had this idea from early on that gravity should bend the path of light. That got some astronomers like Freundlich really excited. We actually follow the paths of light all the time. That was their job. I was their day job, actually the night job. So Freundlich said, hey, I can try to test it for you. And Einstein says, now I'm a big fancy guy, paraphrasing. So Einstein helped to get some money from the Prussian Academy of Sciences for Freundlich and two assistants to mount a new expedition. What they realized is that it might be possible during a total eclipse of the sun, when the moon moves just between the Earth and the sun, blocking most of the glare, like actually happened yesterday, much of the Western United States. So these happen, of course, periodically. So when the moon blocks most of the sun's glare, you could do this amazing eclipse at the text. Whereas when the moon and the sun are nowhere in view, photograph some constellation, some field of stars, maybe the Big Dipper, something like that, and go back and photograph the exact same part of the sky, but when the moon is blocking the sun. But the light being from those distant stars has to travel near these large masses. So you photograph it when the sun is in the way, that should be making this big dent in space-time, like that trampoline picture. The light from these distant stars now has to travel this warped space-time if Einstein's views are wrong. But you wouldn't be able to see that overhead because the sun is so bright, you can't see the dim stars behind it. That's where the eclipse comes in. So you wait for the moon to block the glare of the sun, photograph the same field of stars, and now what Einstein predicts, and Freundlich got very excited about, is the apparent position of the stars should be splayed out. They should be what we now call gravitationally lens, because the light beams are now being bent, much like a lens would do in your head, like a glass lens. So if the actual position is here, it looks like the star has been splayed outward by a amount that Einstein could actually calculate. He could predict. It should be a little bit displaced from the original photograph when the sun's nowhere nearby, and they should be displaced by a specific amount on the sky. Okay, that's pretty cool. That got Freundlich really excited. That Freundlich excited got Einstein excited. So Freundlich says, great, there's going to be a great opportunity, a total eclipse of the sun, easily seen from the Crimea in August of 1914. What could go wrong? I mean, Crimea is a totally quiet place. So it turns out they wound up there exactly as the war broke out. Now they're German astronomers, all these fancy spy equipment, essentially surveillance equipment, telescopes, on the wrong side of the front. They're arrested, their equipment is confiscated, and they're able to do the test. Unlike the Russian mathematician Fredericks, they're only held for about 6 or 8 weeks. Nonetheless, the experiment was scrapped, right? So here's effort number 3, to spread kind of working knowledge of relativity away from Einstein, away from Berlin, hampered at every moment by the right? This is a non-trivial exercise, as we physicists would say. Let me try now an effort to spread knowledge of Einstein's work to the West. It's hard to go east. What about doing the West, towards the West? Well, again, we know from Einstein's letters and diaries and correspondence and so on, that he actually had lots of friends in Leiden in the Netherlands. The Netherlands was a neutral country even after war had broken out. So Einstein, as a German civil servant, could travel to neutral countries. He couldn't travel to Paris. He certainly couldn't travel to London. He could still travel to Leiden in the Netherlands, even after the war was raging. I mean, he did, again, for sort of 1 week, 2 week trips. He had very close friends there, including Paul Ehrenfest, that we show here. It's during these visits, after war had broken out, when Einstein meets and begins talking with a new friend and colleague, Willem de Sitter, who was a Dutch astronomer based in Leiden. And so they would have a chance to have these face-to-face discussions at the blackboard, even as Europe descended into horrible bloodshed. They can talk about the warping of space-time, the effect on the positions of stars and so on. So he begins coaching de Sitter, a world-class mathematical physicist and astronomer in his own right, learning it sort of from the horse's mouth, so to speak. But as Einstein's able to make repeated, lengthy visits and kind of coach his very smart colleague and friend, and de Sitter also gets very excited about this. So there, de Sitter's able to learn from personal tutelage and contact. They have another colleague who's kind of choked off from all of this because of the outbreak of war, and that's Arthur Eddington, another sort of brilliant mathematical physicist astronomer based in this case in Cambridge, England. So by this point, there's a naval blockade between Britain and Germany. It's not only that people can't cross, the mail won't get across, journals won't get across. Just a complete horrible breakdown in communication altogether. So Eddington can't stand at the blackboard with Einstein and hear about these amazing ideas about warping space-time. He's cut off. However, De Sitter, this Dutch guy, is in a position to send mail to Britain and talk directly with Einstein. It's like a little social network that starts forming along with warp space. So what happens is, and we know this from paper trail, that Eddington starts learning about Einstein's work from this neutral character in the middle, De Sitter. De Sitter learns from Einstein. De Sitter writes these very lengthy primers in English. I mean, nice guy, right? So he actually writes in Eddington's own native language to try to get Eddington up to speed. It's like learning this stuff in a correspondence school. It's pretty hard, but Eddington's pretty smart. So he gets up to speed. Now, Eddington, well, I'm very excited about his work for a number of reasons. Not just the heavens are warping and the stars not really are looking at a different spot. Eddington was also a devoted Quaker, a conscientious objector during the war, a pacifist, and that was really hard to be in Britain during the First World War. Many Quakers and conscientious objectors were simply thrown in jail. Others were sent to the front, for example, in France, to help with ambulance service during this horrible poison gas warfare and all the rest. So Eddington, I'd say to his credit, stuck to him and said, arrest me. I believe in my convictions so strongly, arrest me. Cambridge University said, not so fast, that makes us look pretty bad. Right? And so Cambridge higher-ups said, actually, Eddington, instead of having you publicly continue to protest the war effort, what if your national service as a devoted Quaker and conscious objector is to prepare this amazing scientific experiment to test this new idea about bending light? That shows that he had some pretty powerful friends. So his job, literally, instead of chasing ambulances and seeing the horrors of war up front or just rotting in some British jail, his job is to start putting together a group to test this idea that gravity could bend the path of light. Exactly what this German astronomer had tried to do when he was caught in Crimea. Some wonderful books. I'm not Stanley on this again. I strongly recommend lots complicated, juicy story there. So cutting to the chase, Eddington indeed put a whole team together, worked close with the Astronomer Royal and all these advanced fancy scientists in Britain. And the timing is just astonishing. That's what I pause at this timeline. As again, you might remember the armistice that ended the First World War was signed in November of 1918. Eddington had been working for years before then because he knew the next main eclipse where he could get some good viewing would be in May 1990, roughly 6 months later. So preparing ahead of time, the war ends, the big opportunity comes 6 months later, and then it takes he and his team 6 more months after that try to boil down their data and see what their conclusions are. So 1 year after the end of the war, Eddington makes this very, very dramatic announcement back in London, a joint meeting of the Royal Society and the Royal Astronomical Society. And he says, essentially, Einstein was right. The king of English science, Isaac Newton, was wrong. And by the way, we should be nice to the Germans again. Paraphrase. This is unbelievably exciting news all around the world. This is my favorite example, coverage in the New York Times. Lights all askew in the heavens. Eddington had found exactly this kind of displacement that Einstein had predicted. That during the eclipse, the apparent positions of stars really were splayed out just enough to be measured during these in these very, very hard to read photographic flashes. The Times screamed, lights all askew in the heavens, men of science more or less agog over eclipse observations. We should use the word agog much more. Einstein theory triumphs, see the best part. Stars not where they seem or up to be, but nobody need worry. I mean, right. So it's right on the heels of this when Einstein becomes a worldwide star. Why we now have Einstein merch, admitted, we all have Einstein merch, t-shirts, coffee mugs, calendars, right? It's because of this announcement. It's because Einstein's a pretty smart fella, but it's really the drama of this timeline out of Eddington's unbelievable announcement that this very strange sounding idea that space is as wild as a trampoline, that the stars can be splayed all around, and it can be measured during an eclipse. By the way, right after the end of the war, a British team confirming the predictions of the German, seemingly enemy scientists. This is really capturing the imagination. So when Einstein makes his first world tour very soon afterwards, he's greeted in New York City like this, basically almost like a ticker tape parade. Soon after that, he starts meeting actual movie stars like Charlie Chaplin. This is what catapults Einstein, the person, into worldwide fame. Okay. So right around this time, he was giving tons of press interviews. He's talking with the London Times in late 1919, right after Eddington's terrific announcement. And he says, Einstein tells the reporter, today I'm described in Germany as a German servant, and in England as a Swiss Jew. We want to be credit for the Germans.
Should it ever be my fate to represent it as a bête noire if the work actually doesn't hold up? I should, on the contrary, become a Swiss Jew for the Germans, and the Germans have on for the English. And it goes on with a wink, because he was really media savvy. He says, this is yet another application of the theory of relativity. Okay. Well, what was a cute little throwaway line from the reporter became true really, really fast. Again, unfortunately, Einstein's prediction was once again correct. As early as April 1920, just months after this extraordinary excitement, the war is over, this amazing announcement, spring of 1920, some remarkably entrepreneurial political opportunists in Germany on the far right began taking advantage of this worldwide attention of Einstein, who's now this amazing hero of science, to actually start rallying what would actually grow into the Nazi. Okay? So these far-right opportunists, in the midst of this horrible disruption after the end of the First World War, Germany's really in ruins, they start holding rallies not to denounce Einstein, the Jewish pacifist internationalist, that was overdetermined. They didn't like that guy, fine. But actually to denounce the working of space. They hold anti-relativity rallies in sporting arenas and opera houses, attended by thousands of people. It was like going to Foxborough and saying, down with working space time. And Bob was my mom. They would sell out. The headline is really saying for two Nobel laureates, Johannes Schwarz, Leonard, they were kind of political operatives who were doing the real work around the idea, but these two would sort of ascend the stage. And then both these rallies starting as early as 1920, and then picking up speed, of course, as events that we now know about began to accelerate. They didn't only hold in-person rallies, they began publishing like crazy. Philip Leonard wrote these lots of pamphlets, and they became thick books, some of the best sellers. Here's one called also Naturforscher. It's a great men of science, a history of science in biographical form. So Leonard, they were both very early card-carrying Nazis, but once there was a party to join, they joined. They were early adopters, let's say, on Nazi politics. So Leonard wants to prove beyond a doubt that all the most important advances in science have been done by racially pure Aryans. You know, we understand this kind of, we've heard this sort of language, so we heard it. And one way to prove that is to include portraits of the famous scientists to prove, even though they might have had the accident of living outside German lands, they were actually of the right racial stock. So here's a portrait of Isaac Newton to show he didn't have a so-called, Jewish features. It's not, it's not the nicest stuff. So the Leonard and Stark have a two-part strategy. This is the way their argument unfolds. Einstein's work is disgusting. It's repugnant to the Aryan sensibility. I'll say more about that in a second. That's part one. Part two, the most important results actually been plagiarized by properly Aryan researchers. Now just sit with that syllogism for a second. It's disgusting, and we did it first. Okay. So that's how the work unfolds. Let me take that first part. It's disgusting. Here's an example from one of the many countless from this period. The concept of force, which was introduced by Aryan scientists, it wasn't used by people like Descartes and Newton and Galileo, but again, when you get this sort of physiognomy, they were properly Aryan. The concept of force, which obviously arises from personal experience of human labor, of manual creation, which has been and is the essential content of life of Aryan man. So remember, Einstein says there's no such thing as a force of gravity. He gets rid of the idea of force altogether. It's all about geometry, warping, space, and these guys say, well, we proper Aryans, our ancestors worked the land, a very kind of romantic, agrarian thing. We know our muscles ripple as they work the land, and we know what force is, and only an effete Jew, right, would get rid of force. Okay, that's step one. Step two, we did it first. A little German-speaking natural researcher named Johann Solder, way back in 1803, before there was actually a country of Germany, he was a German speaker. He wrote a very clever paper in 1803, which then these Nobel laureates republished in the Gestapo magazine in 1921. He actually used Newtonian gravity, not Einstein, to say that actually gravity could bend the path of light. And so this thing that Einstein's a super fantastic famous hero about, he said, oh, actually that was a proper Aryan researcher, and he ripped us off. Now, it's different amount that it should warp by, it wouldn't have matched the eclipse sector. These are details that the Gestapo didn't pause over. The point is, this is clearly un-Aryan, and we did it first. So now we have a series of pushes and pulls that we're going to remark when they happen in the scientific community. We have this sort of euphoria of Einstein's work. He's really being treated like a hero, right into the streets, these amazing, exciting experiments and observations. And yet, very quickly, this work fails to really kind of take off. Right, so we have on one hand this extraordinary crushing result of when the Nazis take over. In Germany, even then as now, especially then, there was a centralized administration of all universities. Every single university professorship in every German university was controlled by a central ministry. So once you take over that ministry, you have a lot of power over higher education, right? And so they start placing all their favorite sort of politically tested researchers and kicking out the ones they didn't like. So it was an immediate impact on the universities, although the dire impacts that would soon unfold. So you're destroying this the most coherent scientific community that was most pressed to explore this stuff. And at the same time, other new, I'd say, legitimately exciting developments start taking other people's attention, even outside of Germany, like the new quantum theory, like the physics of the atom, like nuclear physics. All these things seem suddenly much more interesting and exciting than this esoteric sounding wobbly space. So you have some really overt changes in political and education institutions, combined with just a lot of other stuff that other people outside of that immediate sphere would think about. Gravity goes nowhere. The study of gravity goes nowhere. So I'm going to pivot now to the second part. Something really dramatic happens a few decades later. So whereas this sputters, it's a huge excitement and it kind of sputters out, here's the Second World War, look at the shape of that curve, right? Something quite dramatic happens already by the early years after the end of the Second War. I'll be quicker. I want to talk about this other more recent episode now. So now we're going to switch again to what really our own backyard. I talk about radar, ballistic missiles, and relativity. And there's another setting in which the community can learn unbelievably important things about relativity, the warping of space-time, not by leaving the messy world, but by being actually thoroughly a part of it. So now I'll talk about some of these developments here in the United States. In fact, even so I'd like to say that MIT joined the Second World War a year before the United States. So you might remember the war broke out in Europe. The Nazis invaded Poland December 1st, 1939. The United States maintained at least an official position of neutrality, helping a lot with the Allies, but not declaring war until after the surprise attack on Pearl Harbor, years later. Right, so Pearl Harbor was attacked on the day that shall live in infamy, December 7th, 1941, 41 years later. Only then did the U.S. formally enter the war. MIT was in a war effort starting September 1940, before the attack on Pearl Harbor, a year before the attack on Pearl Harbor. That was when a British delegation came over. They were now subject to horrible bombardment from both the Luftwaffe and the new B-2 rockets. They were developing very advanced radar, British, but they couldn't scale them up because they were literally under constant attack. They came to the U.S., said, could you please take over the Allied radar efforts, and moved over to MIT. The reason that worked because the president and provost at MIT were at a meeting in D.C. The provost steps out, makes a phone call, says, can we take over a faculty parking lot for this new space for a lab? And they grudgingly said yes, and that's why we can't park, but the war turned out pretty good. We said, give me a minute, don't people, that's how that secret meeting went. And it scaled up to become the world famous RAD lab, a radiation laboratory at MIT. Headquartered first right in the middle of campus, where the parking lot had been, and then outgrowing that space pretty quickly. Tens of thousands of service members came through MIT to learn how to use these new radars. There were dozens and dozens of distinct units that were designed, built, tested, and deployed from MIT. So essential hub for radar for throughout the. I worked on this part, by the way, the wonderful friend and colleague Ben Wilson. So Ben and I were digging into this part. So what happens as soon as the Second World War ends is that MIT leadership and leaders from the Air Force or the Army Air Force and other military branches. So that was a pretty remarkable partnership. We got a lot of work done in science technology for the defense of the nation. Let's continue. So just as the war was officially ending, there were plans being made before the end of 1945 to continue defense research at MIT to benefit the nation. So in December of 1945, the Research Lab for Electronics, or RLE, was founded as an explicit carryover from the wartime radar efforts. So MIT sort of never demobilized after the war, took on new responsibilities in things like radar and other defense-related technologies, literally with an unbroken connection from the wartime radar. Okay. So within a few years, the nature of the presumed threat began to shift. You made radar as one way if you're worried about large fleets of slow-flying bombers. That's one kind of threat to worry about, that kind of World War II planes in the air. But as we know, pretty soon we moved into a missile age. And now you need a different kind of radar if you're about single long-range missiles versus fleets of slow-moving aircraft. Here's a missile being paraded through Moscow's Red Square in the Vision 1950s. So the recent electronics then itself expanded, eventually came the Lincoln Laboratory, actually near here in the Boston suburbs, formally formed in 1954 in the midst or right on the tail end of, say, the Korean War, for example. One of the earliest high priority projects for Lincoln under MIT's auspices at the spin-off defense lab was something called BMUS, the Ballistic Missile Early Warning System. I always found that a funny acronym. It's not a very amusing topic to worry about bombardment by Soviet nukes, but that's what it's called, Ballistic Missile Early Warning System. And this is one of the first highest priority programs from this new MIT spin-up lab called Lincoln Laboratory. The idea was to change the way we did radars to make these so-called pencil beam surveys, narrow radars, scanning the horizon to try to get an early warning of a missile that might have just been launched and might be heading out. So we could get something like 30 minutes warning of an incoming missile attack. That's a very challenging technical problem. It led to tens of thousands of technical reports, many classified, many still classified. A number of them eventually declassified, and so Ben and I were able to go through a bunch of them, much more than we worked in. The point is, this was a huge, huge project with a huge budget, huge personnel, and also huge equipment. So before there was haystack radar, we'll get to see soon, there was this purpose-built millstone radar. It became operational. By the way, here's a pickup truck to give you a sense of scale. Enormous radar dish. You see that? Also built now under the auspices of this new spin-off laboratory. It was operational just as it happens, just in time to be able to ping the Soviet satellite Sputnik, which was launched in October 1957. This is the radar ping from the millstone of the Soviet satellite. That is the kind of environment they're working in, very feverishly around the clock. One of the many, many people to join that effort was this gentleman, Erwin Shapiro, and still with us, still in the area. Erwin had done his undergraduate studies in mathematics at Cornell, did his PhD in nuclear physics at Harvard, and then finished just in the middle of the Korean War, early 1950s. So as he later recalled, he took the first job he could find. He didn't want to get drafted. He wanted to stay locally. So he took a job at Lincoln Laboratory, the spin-off lab at MIT, and was working on one of the sort of subdivisions within this missile warning system. So with his mathematical background, his job was to try to figure out, if you get a few messy data points from radars, how do you estimate where this thing's actually headed? He was worrying about things like trajectories based on a few radar observations of thinking it might be an incoming missile. One part of the sprawling project. Well, how do you know this new complicated system will work if you don't have much practice? Because thankfully, we're not subject to repeated bombardment and so that's a good thing, right? So how do you know this enormous, entirely new system with new kinds of computers, new kinds of radars, new kinds of electronics, how do you know it's reliable? How do you know it's going to work? How do you test the system? How do you calibrate it? So what the very smart folks at Lincoln began to do was invent a whole new field called planetary radar astronomy. Take that huge radio telescope and start sending out beams to the inner planets, to Mercury and Venus, because they're there all the time. They're always available. Right? They're just sitting around. And they calculated, as I said, on a napkin in the cafeteria, it'll be back of the envelope kind of calculation, that the size that Mercury would appear above the horizon, or Venus, is about the same as the size of a Soviet missile that you're trying to pick. So if you can pick out Mercury and Venus with this fancy radar system, you're probably going to do pretty well if you were actually missiles. So the radar, the target size, the cross-section was about similar. So they can practice for free all the time by inventing a whole new field of astronomy in the service of this high-profile defense project. Okay? But if they ever have to worry about really dangerous things coming at us, they can be confident the system will work. You see, all of this correspondence that Ben and I went through from the lab directors to the Air Force who is sponsoring this work, saying everything we're doing is actually to make sure we'll be ready. I mean, in case we're under more serious military attack. And that meant not just the radar system, but every part of very complicated coordinated machines. These were enormous electronic computers that were not very reliable. How do you record the data on magnetic tape? How do you even start processing this stuff? Every part of this had to be worked out, you do your problem shooting, and then practice it by doing astronomy on the inner planets. Soon after that, the group got to use a bigger radar, which again, hopefully you'll see, the haystack radar, again, built by and paid for by the Air Force, run by Lincoln Laboratory, as another tool in this very high-profile, high-priority project of early warning for incoming ballistic missiles. So the lab was now, by a few years in, designing these so-called plug-in modules. This doesn't look quite plug-and-play. Look how big this is. Yeah, but slightly different instrumentation packages. If they're mostly looking for missiles, they're mostly looking for planets. But other parts of the system would stay the same. And again, you see this correspondence between the lab directors and the Air Force who's paying for all this, saying these astronomical studies on Venus and Mercury may have important consequences for the design of future radars for things like how do you tell one kind of missile from another, missile discrimination. And so we have to keep doing astronomy in the service of this high priority defense project, not just playing around looking at planets. We're still trying to figure out if we know when the missiles are coming. Remember, that's in the midst of all that, where this young mathematical physicist, Erwin Shapiro, that's what he said first. Okay, so in the middle of all that, Shapiro attends a briefing on MIT's main campus. I don't know that these still happen. I won't ask Joe until we have a schmear. But certainly in the height of the Cold War, there were regularly held on the main campus classified briefings where researchers will have the appropriate level of clearance because they're working on different military projects for different branches, the Navy, the Air Force, the Army. If they all have the right level of clearance, like you get in a room like this together and brainstorm. Basically, here's what I'm working on. Do you have any ideas? Okay, and you can't do that openly because it's highly classified, sensitive stuff. So we know that Shapiro attended one of these around 1959, 1960, where one of his colleagues in engineering named George Stroke was giving a briefing on a totally separate thing. Stroke was working on navigation for a new submarine-launched missile program called the Polaris missile. He was on a Navy contract, not the Air Force. And his job is to figure out anything that can affect the movement of light, because they were using light for this early navigation. Say more of that. So George Stroke was trying to figure out what things could mess up the motion of light as it moves from A to B. So he does a literature survey. Back then, that meant going to the library and using books. My students have no idea what any of that means. And so he wrote a report by looking at old dusty textbooks, including textbooks in relativity, which have been written decades before. And the engineer finds in the MIT, frankly, fantastic library that actually relativity said, well, all kinds of things can happen in motion with light. You've got to be warping space-time. And so here's this guy working on this top secret submarine launch missile program, suddenly getting immersed, at least a little bit, in relativity and the warping of space and the effects it might have on the motion of light beams. Now that concludes this will have no effect at all quantitatively. Of course it matters, but it's not going to matter right now near the Earth for the launch of submarines. He's doing kind of due diligence. He does the background stuff. Okay, so that's the first time that Erwin Shapiro ever heard of this thing. Shapiro went to Harvard for his PhD. He had never studied relativity, which I always said shows you what graduate training at Harvard is really worth. Something's changing. He was actually quite confident. Relativity was not a headline topic for us. So Shapiro had no idea about that. He learned of it in this classified defense briefing with an engineer friend who had to worry about steering missiles. Okay. But the idea sticks in Shapiro's mind. He says, wait a minute, gravity can affect the propagation of light. I'm using light all the time, right? So what he's doing is he's sending he and his team are sending radar signals, electromagnetic waves, like light, from the Earth. They're routinely pinging the inner planet. They're sending radar to Mercury and Venus and collecting the radar echo. And now we've learned in a totally different context, there might be some really subtle relativity stuff going on there, especially for when the signal has to go to the far side of the sun. Sometimes Mercury is close to Earth, and so the sun's not going to have much effect. Sometimes the radar has to go from, say, a haystack. It has to go near the sun. So now it should be, if Einstein's right, they're one of these larger kind of warps or deformations in that transforming space-time. The signal has to come back, so there should be possibly actually a measurable relativistic effect when the signal goes to the far side of the sun and back. So when quickly writes up an unclassified report, a length report released by the Defense Lab, released as a technical report by Lincoln Laboratory, and then writes a very short, a more cryptic article for the open scientific literature, saying this really might work. We could maybe test Einstein's relativity in a whole new way by using these radars, pinging the inner planets, collecting the echo, and seeing if there's a change in the time it took. Did the light beams travel get slowed down because it had to travel briefly through a phase of more strong space-time curvature? It becomes known as the Shapiro time delay test. When the light beam be slowed down because it went through an unusually warped region of space and came back. Now, in the paper, he shows the radar echo, the return beam, would be a billion times weaker than what they sent out. That's no problem. We have the best radars on the planet, actually, U.S. Air Force. Okay, so he can do extremely careful signal detection. Moreover, the predicted amount of the delay will be 200 millionths of a second. That's 1,000 times shorter than the blink of an eye. That's fine. That's electronics in the world because of the Air Force Space Shuttle. So no other labs on the planet could even try such an audacious thing. He's like, that's my day job. We got it. Great team. Amazing electronics. In the open literature, he can't say too much about why they have these things, but he can say, here's our radar beam, here's our electronics, here's the predicted echo. We really could test Einstein's theory in the midst of these otherwise really high priority, sometimes very scary times. He published that article at the very closing days of December 1964. About a week and a half later, nationwide news, the first major funding cutbacks in science technology since the end of the Second World War. So it's like the worst time to propose a, frankly, very expensive new test of relativity when all of a sudden the funding for all these kinds of tests is about to be scaled back. As a first kind of a quiver in an otherwise very generous phase of funding for basic science technology as well as defense. So now the lab is faced with a pretty significant question: who's going to pay for all this stuff? The Defense Department have actually sponsored their own internal accountants to do a kind of audits. And are we getting a good return on investment by paying for all of this open-ended basic research on universities if our main job is to defend the nation? Is clearly a connection that argued MIT and other places were able to do cool gadgets, but should we actually be paying directly for gadgets instead of paying for open-ended basic research? It's a fair question. And so they began asking this starting in the mid-1960s. They released a final report a few years later that basically said, nope, if we want better widgets, we're going to pay for widgets. We're not going to pay for geeks. Paraphrasing, right? And so this is a huge shift in science funding and science policy in the country, just in the moment when Shapiro is trying to do this test. So now Shapiro's managers of the lab say, oh, wait a minute, now we have to scramble. We never had to ask for money because it was coming limitless supply from the Air Force to keep the country strong and so on. Now suddenly that's in doubt. Now they start boosting Erwin Shapiro's proposed experiment, hadn't been done yet, saying, no, we're doing really good science, get the public excited, pay us after. Right? So I see the lab scrambling, saying the Shapiro test of relativity is of the greatest scientific interest and seems certain to attract wide attention if it succeeds. So now it's become something to put on your posters, to cheer. The lab is not only doing secret, complicated things, we're actually trying to advance the greater understanding of how the world works. Isn't that worthy of support? And they say, isn't that worthy of support from civilian agencies like NASA? But the Air Force has said, you're not going to pay you. So the lab is facing its first real funding challenges again since its founding. So the Shapiro test, which had been a kind of acceptable sideline to make sure the radars worked when the missiles came, that gets boosted up. They actually, look, we're doing really amazing science. We're testing relativity. Please give us more money, including from civilian agencies like NASA. It didn't work, from NASA, but they did actually do that. A little bit extra money from the Air Force, I'm saying mostly of the defense argument. So within a few years, Shapiro and now a growing team were able to actually conduct these tests. They really did send the radar beams to Mercury and Venus, did collect very subtly the timing of their return echo, and they found the data matched Einstein's predictions unbelievably well. During follow-up tests, it became the single most quantitatively precise test of Einstein's relativity to date. So it tells us not only that space-time really warps like a trampoline, it tells us exactly how much it warps. And it warps precisely to the fractions of percent of what Einstein's original prediction had been. So because of the work by very clever colleagues like Erwin Shapiro and this large team at the Defense Lab, we were able to continue learning about the working of space-time, not because this work was outside the flux of daily events, but exactly because they were immersed in changing political realities. Not any conclude here. And the thing about this book on a political history of gravity, I think of politics in a few different ways. Again, I think it'll be back to what Rabbi Fisher was saying. On the one hand, politics means stuff we hear all the time during election season. It's kind of ideologies, it's symbols, it's representation. It's how we kind of characterize our positions, or more often than not, our political rivals. And we certainly see that in very disgusting, hard ways with the early Nazi stuff. It's disgusting, we did it first, but even in more, let's say, happy, triumphant ways. We should all be excited about the heavens. The Shapiro test from this defense lab is going to be great. It's another way of using symbolism to say gravity is actually kind of part of the political story we want to tell. It's a story that we should be delighted to spend money on. It's not only kind of a bad, negative thing, but sometimes it is. So on one hand, it's about symbols and representation. Politics is also about who has access to things, who can get a room together like here, who can share information in letter or now electronic. And that's not always so easy either during the naval blockades of the First World War, when Einstein couldn't even share a postcard with Arthur Eddington, or during the scary early years of Cold War with classification, who could be in a room and brainstorm together, who couldn't be. So politics is not only about symbolism, it's also about who can actually share stuff and who can't, and how we cut off sometimes from each other. And then third, it's about resource and infrastructure, it's about priorities. We're going to spend a lot of money on that, but not on this. And we're going to say, you have access to it. And again, that we see that in the radar story. Shapiro could do brilliant work in his whole team because he had access to the best radars on the planet, the best electronics on the planet, and frankly, one of the best prepared teams on the planet, not first and foremost to study Einstein's relativity, but because of the scary realities of the early Cold War. So that's political too, right? And that doesn't always mean good or bad. It's the realities of the world that he was immersed in. So let me conclude. Einstein's most pristine, beautiful, greatest scientific legacy, the so-called Temple of Relativity. It was built during the First World War. It was rejected in very hateful ways by the Nazis. It was reborn in all kinds of complicated ways during the Cold War and evolved into this day. This was never apart from the flux of human events, right? This was rising and falling with the political tides, sometimes in ways that were very destructive, sometimes in very creative and positive. Even the most abstract theory could not escape what Einstein himself would call the feathers of every tree. Thank you.